Hello, my dear children of faith and good loving of the home of Jesus Christ. Today, we're going to be talking about this series here. It is the sum of values starting at n equals 1 to infinity of 5 raised to the power of n plus 1 over 7 raised to the power of n minus 2. How in the world do we solve this? How do we find the sum of all values to infinity? Well, there's a couple series that you probably learned up to now. Maybe the P series. Maybe you've learned the telescopic series, the geometric series, the harmonic series. What we're going to notice is that this is going to be a geometric series. And remember that a geometric series, just as a little review, I'm going to write a review in red. The geometric series says if I have a constant a times r to the n, and if I start at 0 to infinity, the sum of all these values is equal, or the sum to an infinite number, or to n, is equal to a over 1 minus r. If I increase my index to n equals, for example, 1 to infinity, well, this is a to the r n minus 1 equals our sum. Whatever I increase my index to, let's say this is n equals a, for example, well, then we just subtract a from our exponent. If you want to see a proof for why this is true, please check out a video that will explain that proof to you. It's a really interesting little concept. Alrighty, so now that we have that defined, what's the game plan? If we need to get a to the r minus 1 here, because our index is starting at 1, we want to get it so our first term is just that constant a. How in the world do we do that here? Well, notice for this exponent, for example, 7 to the n minus 2, we need to get this to 7 to the n minus 1, and we can do that with some factoring. Well, 7 to the n minus 2. I want you to think about this using exponent rules. If I have x to the n times x to the n, what do I do with the exponents? I add them together. So this is x to the n plus n. X to the n times x to the n is equal to x to the n plus n. Hopefully that idea makes some sense to you, those simple exponent rules. But notice here, we can use that logic. So if I split this into 7 to the negative 1 times 7 to the n minus 1, well, add your exponents, and what do you get? You're going to get back exactly what you had. So what we can do is actually rewrite the denominator of the series here to 7 to the negative 1 multiplied by 7 to the n minus 1. And that is equivalent to 7n minus 2. Does that idea make sense? Well, what we're going to do next is rewrite the top now. So the top here is 5 to the n plus 1. How can we rewrite that to get it in the similar format where we have a factor of 7 to the n minus 1? Well, let's think about it. I have n plus 1. If I add exponents, if I say, okay, if I want the base of 5n minus 1, what do I have to multiply this by to get this? Well, you'd say it's 5. If I have one factor of 5 to the first, that's going to bring us to n. If I want to bring us to n plus 1, we just simply add 2. 1 to get us to n, 1 more to get us to n plus 1. Hopefully that idea makes sense. 5 squared times 5 to the n minus 1. So notice now our overall series kind of looks like a to the r to the n. We just have to do a little bit of cleanup. So we're going to rewrite this here. Let me grab my calculator. We know 5 to the second is 25. 7 to the negative 1, if we take the reciprocal of that, so this is really saying 1 over 7. If we take the reciprocal, well then we are going to get this into the, it would look like this, 1 over 7 to the negative 1. If we flip it around, this becomes 7 to the 1. Does that idea make sense? So this is 25 times 7 times 5 to the n minus 1 all over 7 to the n minus 1. we're allowed to split this up here and say, okay, this is really this times this. And now you should be able to see that we have a times r to the n minus 1. Let's take 25 times 7. That's going to be 175. This is our a value. Alrighty. And then I want you to notice, and I'm just going to erase this here for simplicity. But notice something really interesting here. Remember our exponent rules. If we have a common power, we can pull it out. Right? If I have some value a over b to the n power respectively, I can write this as a over b to the n power. Notice that this is true. If you don't believe me, do like 1/2 to the third power and plug in values for n and plug in a value here for n, and you will get the same answer for both. You'll see that the equality is true. So what we're going to do, we're going to apply that knowledge of exponent rules and rewrite this as 5 over 7 to the n minus 1. So what this simplifies to is 5 over 7 n minus 1. This is our r right here. So remember what I said about the sum of the geometric series? That's equal to the sum of all numbers in this series. And I'm going to rewrite 5n plus 1 over 7n minus 2 is equal to a over 1 minus r. Or in other words, this is equal to 175 over 1 minus 5 over 7. What's that equal to? Go find it in your calculator. See if you can beat me. I'm a little faster than all you guys, obviously, because I'm that cool. We're going to see that it's 1,225 over 2. That is the sum of the series for this geometric series here. Alrighty, so let's just do a little recap of how we went about solving this problem. We noticed that we have something that kind of looks like the geometric series, that weird variable, or not variable, constant to some power n minus something. Okay, we did a little bit of manipulation using our knowledge of exponent rules. Then we got it into the form of the geometric series, okay, by using this a times r to the n minus something, right? We just had to do a little bit of rearrangement. Then we used that idea that we know that the sum of all the numbers in the geometric series is equal to a over 1 minus r. We then plugged in values for a and r respectively, and we got a value for the sum of all of our values in the series. I hope you guys enjoyed. If you did, please drop a like, comment, and subscribe, and I hope that you have a wonderful day.